In this video, we're looking at calculus induction. Now, this one's not overly common, but it can occasionally come up, so it's worth mentioning. Be sure before you do this that you've practiced all your rules for differentiation. So that could be product rule, quotient rule, and chain rule, as well as all your derivatives of common functions. So that's polynomials, e's, logs, and trig functions. So we're going to do this one with an exponential function here. So we'll be using derivatives of e's essentially. Just as a little recap, if we have f of x being, if we have y being e to some function there, then dy dx is going to be e to the power of that function times the derivative of whatever was up the top. So that's sort of the rule that we're going to be using here. All right, so let's apply that to this one. So if f of x is e to the power of 2x, then the derivative there is going to be the same thing. And then we're just going to be timesing it by 2, which is the derivative of the stuff that was up the top. Now, generally, if it's just a number, I like to put it out the front. So we'll just keep the 2 out the front there. Next derivative down. Again, we're just going to be leaving the 2 as is. And then we're going to be doing the derivative again. So another 2 will come out the front. So where this 2 came from here, that was the derivative of the stuff up there. That's where that one come from. Okay, next derivative down. F triple dash of x will be 8e to the 2x. And once you've gone past 3 dashes, we don't really bother writing it anymore. We just write the number, like which number derivative it is. So f4 of x is that. So we can actually make a conjecture here. You might notice with the numbers out the front, this number here, the 4, that is 2 squared, 8 is 2 cubed, 16 is 2 to the 4. So in fact, our conjecture is pretty much written for us. It's going to be 2 to the power of n e to the 2x. That will be our derivative. Okay, let's formalize this with a conjecture around it. So conjecture. Now we can say if f of x is e to the 2x, then, should give myself more room, then that is true. Okay, so for all n in z plus. So we're going to prove this using induction. So first thing we're going to do is let Pn be the statement. So Fn of x is 2n e to the 2x. And then we're going to look at P1. So P1, f dash of x is 2 e to the 2x. What I might do is I'll just reiterate that f of x is e to the 2x. Therefore, f dash of x is 2 e to the 2x. So this is by your rules of differentiation, or if you want to be really specific, you could say that it's by the chain rule. And then over here, we expect it to be 2 1 e to the 2x. Cool. So that is what we would want. So, yep, that's correct. Therefore, P1 is true. Okay, next step. So we're going to assume that fk of x is 2 to the k e to the 2x. Wonderful. Now, let's see if we can do our pk plus 1 step. Pk plus 1. So we already know that fk of x is 2 to the k e to the 2x. So that's star, and then that should say for some k in z plus. So we know that this was 2 to the k e to the 2x, so therefore f of k plus 1 of x is 2 to the k will stay out the front, and that is from the chain rule. And then what we can do is we can just multiply 2 to the k with 2. So this is 2 to the k plus 1, e to the 2x, and then this can be your index laws. Just explaining everything we're doing so that it is very clear that we sort of understand how that proof works. Let's do our want to show. Our want to show was that f of k plus 1 of x was 2 to the k plus 1, e to the 2x. So we have actually got that want to show. Cool. That is good news. So therefore p of k plus 1 is true. Therefore, by induction, fn of x is 2 to the n e to the 2x for all n in z plus.